because we have quite tight timetable. So let's not start without delay. So today we have a second series of presentations on different deep learning research, and in total we have 12 talks. So that's why I ask every presenter to tightly respect the 10 minutes limit in order we can do everything on time. So I guess we make first, say 6 presentation, make a break, 10 minutes break, and then continue with the remaining ones. However, I also ask you to actively participate in a discussion on all the papers, on all the presentations, and ask questions in chat, either in chat or by voice after the talk, in order we can actively discuss all the presentations. And I suggest to use the same order of presenters as we have in our Google table. So the first presenter is Georgy Kormakov. Okay, let's start.
Okay, anyone hear me? Everybody, yeah?
Yeah.
Okay. Oh. Yes. So, hi everyone. My name is Georgy, and I want to present emergent complexity and zero-shot transfer via unsupervised environment design. When I read this article, I want to answer 4 main questions. First of all, what is the problem of what this method solve? So, because of many reinforcement learning problems such as robustness, transfer learning, unsupervised reinforcement learning, and emergent complexity require specifying a distribution of tasks or environments in which policy will be trained. We should use some kind of distribution on these environments. For example, if we try to simulate a robot to pick up objects from a bin, we could use any possible configuration of objects, but if we try to set some kind of distribution over the object position, the task will be solved. But this approach has several disadvantages. For example, it's creating of useful one distribution is error prone because of some human factor or because it takes significant amount of developer time or effort. Well, it also hard to automate, but the main reason why it uses until today, because it's easy to implement if we know some set of distribution. But alternative approach is unsupervised environment design. It can vary only set of the environment parameters. Almost there are no human factor because it automates learning process and some kind of and makes some kind of curriculum or plan of learning. But it's really hard to provide high quality diversity of environments, and that's why. First of all, let's call under specified environment an environment that has 3 parameters which control features of environment and its behavior. Then we describe unsupervised environment design like problem when we take this underspecified environment and current policy, and produce some new distribution of fully specified environments in which that policy can be further trained. So the main problem in this definition is that we should generate new and interesting fully specified environments. And how was this problem solved? First approach is simply randomization approach, or randomized approach. Designers specify some set of parameters to which policy should be robust. Then they randomly sampled from this domain for each episode, and then policy trained that performs well on average cross values, parameter values, yes. Well, it's easy to implement. It really works in some real case example, like in-hand manipulations, but it still requires careful parameterization and doesn't guarantee it good and informative performance in some specific configuration. And that's why the next approach is an adversarial or multi-agent training. So there are several approaches. The main is Minimax adversaries. The main goal of this approach is to adversely generating environments to minimize the reward of the current policy. So we have some agents that have their own reward that he or it produce new policy. Well, yes, there one approach that important, curriculum learning. We have teacher reward, what is computed based on whether agent takes more or less steps in navigation problem, for example, that will be briefly discussed later. And then we threshold some cumulative reward on this problem and increased this threshold over the time. So let's discuss disadvantages of this approach of Minimax adversarial and also domain randomization. As I said, in domain randomization, we produce two simple examples, but in Minimax adversarial, we could completely make some completely unsolvable environments. And in this article, what I read, their new approach is called paired. That the main ideas of that is we have main agent as a protagonist and opposite agent as antagonist. And the main solution or main idea of this approach is to have environment adversary. It designs new environments in which antagonists achieve high reward, but protagonists receive low reward. And then if we produce some unsolvable environments, both players perform the same, but this environment gets 0 score. And that's why it's very efficient. Briefly discuss some new definitions. First of all, partially observable Markov decision process, their actions, observations, states, and so on. But the new definition is underspecified partially observable Markov decision process. So the main idea of this underspecified decision process that we have 3 parameters, as I said, of environment that we could vary. And if we want to make some specific partially observable Markov process, then we use set at environment parameter theta and make this decision process with this trajectory of environment parameters. Well, and with this definition, we could define our environment design approach. So if we specified environment policy that produce from policy new set of possible sequence for environment parameters, then we could solve our task. There are several examples because this problem has been studied in decision theory under the name of decision under ignorance. There are several environment policy. For example, domain randomization, it's a principle of insufficient reason of Laplace, and so on. And in this approach, it is Minimax regret. What is this? Let's describe the implementation. Regret is defined as a difference between the payoffs of two agents. And if we have antagonist and protagonist, we only have regrets like this. And after setting the antagonist and protagonist, we sample new environment parameters from a set of distribution, and then make some iterations through trajectory of for policy of protagonist and antagonist, compute the reward, and make optimization for protagonist. It's maximization of inverse regret, and for antagonist and adversary policy, it's maximization of true regret. And what is the theoretical foundations of this approach? Well, if we have rewards like two separated sets, like this, then this approach takes a policy which always succeeds on some parameter of environment, minimax regret. So, and the next theorem said why this is so, because if we have tuple of policies and environment parameters being in Nash equilibrium, and if this situation is jointly a best response to policy of protagonist, then policy of protagonist is a solution of min-max optimization. So, and why this research is important? First of all, it really increases emergent complexity, because if we have a number of blocks and distance to goal in navigation problem, then we see that paired approach is the only method that continues to increase number of blocks and distance to goal. So it varies complexity of the task. And also it could be seen in passable path lengths and solved path lengths. It also improves zero-shot transfer. So if we don't see in training some kind of situation, environment like this or this, we in several approaches like randomization or minimax, we couldn't solve this problem. And on the only one approach is a paired approach that have ability to generalize it to transfer tasks. And one also main important reason, that these techniques lead to more efficient ways to building robust systems, and it automates some generating new and challenging environments for detecting some troubles in the training phase, not in deployment settings. Well, that's all. That's about all. Thank you for attention.
Okay, thank you. I would say that you have chosen, well, too abstract, too general view to the methods, to what is going on, and there is certainly a lack of a particular examples. Could you please provide just some example of particular environments? What are these parameters that we can control, and how we can learn the agent in this environment?
So let's make some new example. Yes, I described this example, but in this example, we, for some reason, only can vary empty blocks and blocks with some edges or that wall that produce in the map.
And we need to, well, to find an exit from the labyrinth. So what is the task? Or to go to a particular point?
We should go to a particular point, like triangular is a start point and rectangular is a finish point, and we could make some map or make some road to this finish point. Well, and in this task, we in trainable phase, in train phase, we have to make some examples of maps. If we set parameter of this environment like empty blocks, there are no internal blocks like walls or something like that. And if we increase the number of blocks, for example, 50 in this picture, we have to solve this problem efficiently like it was empty. And main reason why we should use paired approach is that because we can vary this parameter and unsupervisedly, not randomly or solving adversarial problems, because adversarial should produce unsolvable situations in this task. But paired could produce new and interesting configurations that were not in the previous environments.
Okay, and well, what are good and what are bad environments that can be generated by the algorithm?
Well, in this situation, the main goal is to have improving for zero-shot transfer. It's like if we learn only in these configurations, like sampling points randomly or with paired, then with this approach, we should solve and these tasks like labyrinth or hard to solve problems.
So we just want to quickly learn a new environment, in new corridors faster than if we try to learn this corridor from scratch. Yes.
Yeah. It's one reason that why use paired, and also it increase complexity of the system. Like this, we have many configurations in training that are not a random structure. But in this algorithm, we see that in training phase, we vary complexity of the environment, and that's why agent could solve these tasks in 20 or like 17% of all.
Okay, so you should start with something like this from the very beginning of your presentations. Just let's consider this type of problem and then put all the formulas, because otherwise it was too hard to understand what's going on with such an abstract view. Okay, thank you. Let's switch to the second.
Yes, I have a question. Can you say who is where is protagonist and where is antagonist? Because like I just don't see the two players in this game.
Okay, in this game you couldn't see some protagonist and antagonist because they are existing in the train phase. We set an agent that solve these tasks as protagonist, and the same agent that solves the same tasks as antagonist. But protagonist is maximizing this regret, so it's inverse of difference between this utility function. And antagonist only maximize the same regret, but not the inverse.
Well, does that mean that the antagonist want to solve this task in the most hard way? Like, what's the point?
The point is that adversary policy or yes, adversary environment produce new environments that are hard to solve for protagonist, but antagonist could solve this problem easily. And if antagonist could solve this problem easily, then regret will be maximal for them, but minimal or negative for protagonist. And that's the goal of an adversary and antagonist players.
Okay, so basically we want protagonist to be as good as antagonist, yes?
We want to protagonist could solve more complicated or more complex problems than antagonist, yes, and that's why we should maximize this with adversary.
So in antagonist, we go from the from our goal box out as far as we can, and our protagonist tries to move to our goal point from a far point. Yes, and it can be a case that well, if it is easy to go far from our goal box, it means that it may be more easy for a protagonist to go from far point to the goal. Yes?
Well, yes, antagonist should antagonist like know the path between very yes, between two far points, but protagonist doesn't know these points and should use some training for finding the optimal path, something like that interpretation.
Okay. Okay, let's move to the second talk because we already discussed this too much. That is because of your presentation, which was, well, not quite unclear of what is going on inside.
Well, it's because this approach could implement for robotic or another one reinforcement learning problem. That's why I start with a common situation. I'm sorry.
Okay, so the next speaker is, well, Fedor Lebedь. Please.
Yeah, I'm here. Wait a bit. I will share my screen. Oh, no, front screen. Okay, I hope you can see the screen. The topic of my annotation is every model learned by gradient descent is approximately a kernel machine. In the article, it will be shown that every neural network, which is learned by gradient descent, standard gradient descent, is to some extent equivalent to a kernel machine. It's worth mentioning here that by neural network, they really mean any function differentiable to some set of parameters, because there is no dependence on the layered structure of network whatsoever in the article. So let's see this formula. Yeah, sorry. Give me a second. Yeah, let's see a formula. This formula describes a typical kernel machine, but it differs from canonical kernel machines because the weights of the kernels are dependent on the argument of the function. But the authors chose this form because it is more interpretable in terms of this article than the canonical form of kernel machines. So before we discuss the main results of the article, let's discuss some preliminary terms which are necessary to understanding the nature of the theorem which will follow. Firstly, let's introduce some kernels. The first one is the tangent kernel, which says how 2 points are equal in terms of the gradient of the network at some point. So the next kernel is the path kernel. Let's suppose that we have a network trained, and so there is a path that the network weights have traveled during the training. Let's take the integral over this path and integrate over the tangent kernel. That also would be a kernel because it's a sum of kernels. And this one is called the path kernel. The last kernel which is mentioned in my slide is relevant to the different representation of the results. So they also mention this kernel, although it's not a real kernel. So it's the same as the path kernel, but weighted by the anti-gradient of the last function with respect to which the gradient descent was done. Okay, it's good to mention that usually these kernel functions, it's not obvious what is the mapping into the feature space would be for that kernel. But in this space, they know that the representation of a given point is in the straightman space, and it is the mapping from time to the gradients of the network at the point of the weights during the training at this time, and this point in the parameter space, but not the parameter space of the network, but parameter space of the objects. So let's continue to the next point, which is about how the theorem will be derived. The theorem will connect the kernels with the gradient descent, so it is obvious that we will need somehow to connect the differential equation, which is now stated in terms of integral, but it is equivalent to some differential equation, and the gradient descent, which is a finite difference scheme. So let's note that if in finite difference scheme we make the grid diameter go to 0, the scheme will be effectively equivalent to the differential equation on some finite segment. So if they take gradient descent and make the learning rate go to 0, the resulting differential equation is that resulting differential equation can be used to state a flow in the network parameter space, and this method is called gradient flow. Here the gradient flow equation is. So we will be using gradient flow to prove the theorem which will show the equivalence of neural networks and kernel machines. Okay, let's state the main result. And the main result is the following one, that any function can be expressed as a sum, that any function f at p can be expressed as a sum of this function with some random parameters plus some sum of path kernels weighted by some function a's which have this particular form. The first equation is the restatement of the second equation, this one, but this is a kernel machine because the weights are zeros and do not depend on the argument of the function. But it is less interpretable, so the authors decided to use the second equation as the main result for their problem. This equation can be easily derived if they use the integral equality for function that f at x equal f0 at x plus some integral over time with the difference in the and if they substitute the gradient flow equality and the definitions for path kernel, we will obtain these equations, and math isn't that complicated. But it is worth mentioning that it is essential that the gradient descent and not some other optimization scheme like Adam or Hermann's-Prop is used, because the kernel should be symmetrical, and it is only obtainable with gradient descent formula. Okay, let's say some remarks about the given equations. It is stated in the article that the equations can be generalized to account for batch stochastic gradient descent, where they split the training set into batching. And they say that the formulas do not become extremely complex, but the path integral becomes a stochastic integral, so there are some problems. And also, if they add a regularization term for the network in gradient descent, in the path generated by gradient descent, then the formulas are also valid, but there is a term added to the this term, which form is fairly complicated, so I decided to omit it in the annotation. And the final point is that the authors claim that usually in machine learning, the neural networks are learned with the learning rate small enough so that the gradient flow becomes equivalent to gradient descent, but they do not provide any proof whatsoever for this claim. So that's all for the article content. Be free to ask questions.
Okay, thank you. So why your topic in Google table was gradient descent is bad for ML?
That's because I was creating some hype for my article, and because I've read only an annotation, and in the annotation it seemed like they would criticize the gradient descent, so I made my stakes, and as it turns out, it was a miss. Okay. They do not state if whether it's good or bad that the gradient descent produces the neural networks which are equivalent to kernel machines. They state that those kernel machines would be impossible to compute using classical algorithms for kernel machines. But they do not say if this class is small enough or it's big enough. They just say that it's just another interpretations for what neural networks are.
And what are the practical benefits of such representation? Okay, we show that we can interpret neural network as this second formula, and what we can infer from this? Can we infer some theoretical results or what? What are the benefits?
Although the article does not list any benefits, they say that it is a means for better understanding neural networks. They say that the result shows that support vector machines, which are usually quadratic, they use quadratic parameters in the during the computation, because we need to compute the Gram matrix. But with training sets large enough, for example, a million objects, like in typical neural, let's say, image processing, they can compute those machines, but networks are able to somehow deeply incorporate it into their relatively small set of parameters with respect to the training set. They each will implement this kernel machine, but they do not provide any means to speed up existing algorithms or do something with them.
Okay, it seems like this paper was not accepted for some good conference.
Yeah, and the text was not really good, but the result were pretty interesting in the theoretical point of view, so I decided to present it.
Okay, anyway, the presentation was quite short and clear, so that was very good. Okay, thank you. Let's move to the next presentation by Timur Kinazarov, please.
Hello. Okay, сейчас. I will tell about speaker authorization with CLSTM. This paper is from Google Engineer, and a lot of images, it's from another presentation.
I'm sorry, Timur, could you please speak a bit more louder, because now it's too silent.
Okay, like this?
Continue, it's not clear. Is it better or not?
Okay. For example, like this?
Oh, yeah, super.
Okay. Okay. For example, first of all, what is the speaker diarization? It's a process of partitioning an input audio stream into homogeneous segments according to the speaker identity. It solves the problem who spoke and when. It can help improve speech. Okay. Within a basic understanding of this recognition technique, let's take a look at the anatomy of the speaker diarization system. First of all, there is a voice activity detector, or VAD, that detects the speech part from the audio and remove noise and other non-speech parts. Then we need to extract segments from the speech such that both the segments contain only a single speaker. Next, we need to extract embeddings from each segment, I vectors and D vectors calls in this paper. After that, they have embeddings and they cluster them to determine the number of the speakers and each speaker time steps. And here is a diagram of their system. After a voice activity detection, they extract a fixed length sliding window from the audio and run their LSTM network to produce D vectors for each sliding window. It's a process of and after aggregation, they cluster these segments embedding to produce the final diarization results. Now they tell a little about embedding Here is the diagram of the D-vector system. Once they have a fixed length segments of audio, they fit it to a neural network. In this case is LSTM, and the output use as embedding called the D-vector. In this case, the loss function for trained D-vectors used generalized end-to-end loss. They train a model on batches, and for each embedding, they only look for distance to the truth speaker centroid under the distance to the closest false speaker centroid. And they say that this loss much more efficient than other loss functions for this problem, for solving this problem. And in this paper, embeddings trained with this method. Next is clustering algorithm. They have two methods, online and offline. For online clustering, once they receive an embedding, they immediately assign a speaker label to these embeddings. This is really useful for the real-time application, but the accuracy is really not very good. For offline clustering, they first wait until they have all embeddings of the entire utterance, and then they running clustering algorithm and assign speaker labels to these embeddings. And at the same time, over the clustering, they have much more latency and better results than offline clustering. They have two online clustering algorithm methods, system for their generalization system. The naive online clustering algorithm and the links online clustering algorithm. First, it simply applies a fixed threshold on cosine similarities. It basically considers the additions as a dynamic and continuous speaker verification problem. Links clustering is much more complicated. It's how they say, it's anisotropic, probabilistic, and generative method. It was originally developed for phase clustering. For offline clustering, they first try k-means. They use k-means plus approach for initialization and use the elbow rule to determine the number of clusters. There are both standards, how they say, practices for k-means. And there is a lot of problems. There is a lot of problems of speaker diarization. Here they are saying about some data where we can see problems. So, for example, it's non-Gaussian data where we can get wrong cluster, or with problem with gender or age and race effects. In this slide, we can see that two male speakers is closer to between, and female is not near there, but we can see wrong clustering between two different speakers with male person. And here they say about overlapping speech creates overlapping speech here, yeah. Offline clustering, they call in spectral clustering. They call spectral clustering. In it, first step is constructing affinity matrix using cosine similarity between embeddings. Then they apply a sequence of refinement operations on the affinity matrix. First, they apply a Gaussian blur to the matrix. This is used to smoothen the data and reduce the effect of outliers. Then they apply a threshold to each row of the matrix. This will zero out affinities between different speakers. In third step, the symmetrization operation follows to restore matrix symmetry after the threshold. The diffusion operation is used to sharpen the boundaries of distinct speakers. Finally, they apply a row-wise max normalization to avoid some undesirable scale effects. If we want to see how it works, in this slide, it shows with formulas. For example, if we know first three operation, and fourth diffusion, it's like just multiply x by transposed x, and row-wise max normalization, it's by this formula. And here is a diagram of their refinement operations. They say that here we can see the threshold is the most important operation here. By these operations, we have two parameters that should be turned on the dev data set. The Gaussian blur kernel size, sigma, and the row-wise threshold, p. And they say that using a hard threshold gets to avoid having too many zeros in the affinity matrix, which may crush final k-means algorithm. To find the number of clusters, they use the Eigen gap. And the optimal number of clusters should maximize the gap of eigenvalues. In this gap has max value when k is 8. That's how special clustering overcomes the failure cases of k-means. In these slides, it's in this image of authors, we can see that they saying that the problem is solved like this. For non-Gaussian data, imbalanced clusters, and overlapping speech. Okay, by this operation, okay, the biggest the difference between the evaluation of diarization and the evaluation of their systems is that matrix must be permutation invariant. For example, the sequence of speaker label ground truth is ABBCA, and the hypothesis sequence of speaker labels is CAABC. They are actually equivalent, and which us need to make speaker A to C, B to A, and C to B. The solution to this permutation invariance is that before computing errors, they first need to find an optimal speaker mapping between the ground truth and hypothesis. Founding this mapping is just this, how they say, is just a standard assignment problem and can be solved with the Hungarian algorithm. There is two types of error. Early introduced by the noise activity detector and the segmentation in this part.
Timur, you're already out of time. Please come to the end.
Then they are overlap the speech, and finally this is a confusion error, which means one speaker was mistakenly labeled as another speaker. And function of diarization error rate, it's just sum of all these errors. Okay. and they are trained in this data. And if we can see this table of results, we can see that D vectors and spectral method works better than all. And in the final model of in this paper, they say that the best model is text-independent speaker verification with trained with generalized end-to-end loss, 3 layers LSTM running on sliding window, and using Eigen-gap to find number of clusters and a sequence of refinement operations on an affinity matrix. Okay, that's all. Thank you.
Okay, thank you. Due to the time constraint, only one question from the audience. Maybe. Does somebody have a question? Okay, I have one. Do they consider detecting the number of clusters in online mode? So if you are processing your data online and, well, you determine you have some particular set of clusters, and then a new speaker is added to the data and they add a new cluster. Did they consider this scenario?
About online. I didn't have a question.
Okay. Thank you. Let's move to the next talk by Дарья Петренко, please.
Да, здравствуйте, меня слышно? Сейчас я экран шарю. Так, видно презентацию?
Yes, we see the presentation.
Okay. Sorry for my Russian. Now I'm going to start. Today I want to speak about text-to-speech synthesis. And first of all, I want to give some information about what forms can be sound presented in. In order to measure sound, air pressure is measured with some fixed frequency. It is often 44,100 samples per second, and what we get is called a waveform, and it can be easily written into a file. From school physics course, we know that audio signal is a superposition of several single frequency sound waves, and what we get by measuring air pressure is their resulting amplitude. But there is a method that allows us to decompose it back into individual frequencies and their amplitudes. And this method is Fourier transform, and it allows us to move from time domain to frequency domain. So for each frequency bin, we get a mean value of amplitudes of waves with such frequencies, and the whole histogram is called a spectrum. But in our case, signal's frequency content varies over time. So a way to represent such a sound is to compute a spectrum for each of overlapping windowed segments. And what we finally get is a bunch of 2D histograms. And in order to represent all of them in one image, we show one of the dimensions, the amplitude dimension, in color. So the example of such a spectrogram you can see on the slide. But there is such a fact that humans do not perceive frequencies on a linear scale. It is easier for us to detect differences in lower frequencies than in higher frequencies. So the detailed information about higher frequencies is less useful and less informative for us. So a MEL scale was introduced. Equal distances in frequencies converted to such a scale sound equally distant to the listener. So MEL spectrogram is just a spectrogram where frequencies are converted to MEL scale. And this is a kind of spectrogram that is commonly used in some tasks. Here is a brief structure of most of TTS synthesis pipelines. First of all, raw text is converted, maybe via some preprocessing steps, to a sequence of graphemes or phonemes, and the acoustic model takes this sequence as an input, and it outputs a MEL spectrogram, which is an intermediate representation of our result. The vocoder model takes a MEL spectrogram as an input, and it outputs a waveform. Some popular vocoder architectures are based on normalizing flows, but the main topic of my today's report is acoustic model. I want to tell the brief ideas of some approaches that are popular. And the first idea is represented in Tekkatron-2 architecture. And it is just RNN encoder-decoder architecture with attention. So nothing interesting. So let's move on to another approach. An autoregressive approach is very time-consuming during both training and inference. So another idea was introduced in a paper called Fast Speech. This architecture works much faster, and it is a feed-forward structure based on transformer self-attention and 1D convolutions. So FFT block that you can see on the scheme contains multi-head self-attention and 1D convolutions, and some layer normalizations and residual connections. So both encoder and decoder are bunches of such FFT blocks, and the input and output shapes of FFT blocks are the same. So there is a problem of length mismatch between the phoneme and spectrogram sequences, because each phoneme results in several frames of MEL spectrogram. And in order to solve this problem, length regulator is used. The explicit durations D of phonemes are used, and length regulator expands the hidden states of the phonemes D times. So during training, the ground truth phoneme durations extracted, for example, from the attention layer of autoregressive model from the previous slide are used. And during inference, these durations are predicted from encoder output by a special model called duration predictor that is trained together with the main model using teacher forcing. Not all characteristics of the resulting sound are contained in input text. And to deliver human-like speech, the TTS system must learn to somehow model prosody, a bunch of implicitly, or a bunch of phenomena in speech, such as intonation, stress, and style. And in order to address these issues, the global style tokens layer was introduced. It is a bank of embeddings that are trained together with the Tekkatron-2 model. And during training, the ground truth MEL spectrogram is passed through the reference encoder layer. It is RNN model that compresses a variable length order signal into a fixed length vector that is called reference embedding. And the reference embedding is passed through a style token layer, where it is used as a query vector to an attention module. The similarity of this vector to each of the bank of randomly initialized embeddings, which are called global style tokens, is computed. These tokens are trained, so the module outputs the weighted sum of these tokens, which is passed to the text encoder for conditioning at each time step. And this GST layer is jointly trained with the rest of the model, driven only by the reconstruction loss from the Tekkatron decoder. And during inference, an arbitrary reference passed, or the weights can be even manually chosen. And there is one more article that suggests to predict GST weights or even raw samples from the obtained space of GST embeddings from the encoder outputs. And so the GST embedding here is passed as an input to a GST decoder or to decoder. It is added to encoder output and passed to a decoder. So that's all for today. Thank you. Any questions?
Yes, thank you. Any questions from the audience, please?
Yes, about diagram correction, how we get the MEL diagram. We treat the spectrum as a distribution? What I mean, when we want to determine the frequency at a specific time, we take the relevant time window, we compute the frequency, and we take the expectation of them. Am I right?
What expectation? We take just here when we apply a Fourier transform, and we get amplitude for each frequency. So we get a histogram, and here we just each histogram is a table or is a column in this table. We take just mean.
Okay, so when we get MEL diagram, we just map the existing histogram into the new histogram.
Yes, so we just move. Here we have a logarithmic scale, and here we just move to another scale. We just rescale the values we have. So
yeah, okay.
But this scale is MEL scale.
Yeah, I was just thinking how that netting makes some points more important than the others. That would make sense if the amplitude acted as a probability, so I asked. Okay, thank you.
I have a question about the training data. Am I right that we need, like, as our train set, a text, an audio, and we should split in audio into segments, and each segment is for each phoneme of like for a phoneme in our text or something like that?
So. We need a text and an audio where this text is spoken, and do you speak about the durations?
Yes, I'm actually speaking about durations, like how we can.
Here, we don't need to manually extract the durations. We take an attention layer from this model. So for each input phoneme, we have attention weights, and we apply some algorithm, for example, some dynamic programming algorithm to map each spectrogram to the phoneme. So using these attention weights. So we have a picture like this, attention. So we don't need to manually extract the durations. We extract them using some algorithm.
Yeah,
so
okay.
First of all, we train autoregressive model, and then we use the attentions from this model to train FFT model.
Okay, thank you.
One more question. What are these specific layers that are used for speech processing that are different from our standard layers like convolutions, linear layers, and other things? Do they use something specific in their architectures?
In these models, there are no such layers, but there are some models where, for example, speech predictor layers is used. For example, in model fast speech 2 or in model fast speech, there are some layers that predict F0, which is a pitch, which is the частота колебания голосовых связок from the input, from the encoder output. And it is concatenated with the encoder output and passed to decoder. And for example, GST layer is something specific for speech synthesis.
Mm-hmm. Okay, thank you. Let's move to the next talk by Pavel Lukyanov, please.
So, do you see my screen?
Yeah.
Okay, let's start. My name is Pavel, and I would like to tell you about speech and paging tasks. So I want to say how we can work with audio data in deep learning. So we have raw signal, time and amplitude scale, and after several transformations, Fourier transform with applying window functions such as Hamming, we can get spectrogram. And then we translate spectrogram into Mel scale, so we get Mel spectrogram. Later, this spectrogram can be processed from convolutional neural network, and so in the conclusion, we can work with audio data like image. So I want to go to say about speech impaging tasks. In the slide, we can see examples of speech impaging in our signal. There are parts which can be there are corrupted parts, degraded parts, or missing parts. Missing parts we set to 0 value on spectrogram. Also, there are some ways to corrupt our signal, such as adding noise, and then we can to improve our signal, and speech impaging is task of improving quality of our signal. So we need to tell about speech VGG. It's a feature extractor for speech processing. In the slide, we can see architecture of speech VGG. It's the model adopts VGG 16 architecture. The network is built out of 5 main blocks, each composed of stacked convolution layers, followed by ReLU activation and concluded by max pooling layer. the output from the last convolution layer is processed from fully connected layers, and in the end we apply softmax output layer. And in our task, we need information only from this 5 output from these 5 blocks. So in the speech and painting task, we use next architecture. That's our deep neural network was applied to restore missing or degraded parts of the log magnitude of speech STFTs, and this architecture is based on UNet. Our architecture was composed of 6 encoding and 7 decoding blocks. Each encoding block consists of 2D convolution layer with stride 2 and ReLU activation, and each decoding block upsampling its input from 2D upsampling layer with kernel size 2. And the outputs concatenated set of features was then processed through to the convolution with leaky ReLU activation. So batch normalization was applied after to the convolution layer across network. And to train our model, we need to use speech VGG like feature extractors, so deep feature loss training, and then reconstructed and the original signal when process from the speech extractors and activation here of all of 5 extractors. And were obtained for the reconstructors of reconstructed signal and original signal samples. And deep feature was computed. Deep feature loss was computed as L1 loss between 2 representations. So what we can see on the slide, I would like to tell about implementation details. The speech VGG was pre-trained using cross-entropy loss 50 epochs with learning plate and constant learning plate. Each considered configuration of the UNet for speech and painting was trained 30 epochs using the feature loss with a fixed learning plate, and thereafter used the Adam optimizer. So the results of the experiments are on the table. You can see that this developed framework is show better results than over baselines. For example, in VGG used VGG 16 pre-trained on ImageNet. There are 2 metrics. There are 2 metrics and PSQ to compare our reconstructed signal and the original signal. And in conclusion, what I told about speech and painting tanks, and there are references to the original articles. That's all. Thank you for your attention.
Okay, thank you. Which data was used for training deep VGG network?
Okay. I forgot to say all experiments performed using LibreSpeech dataset, open dataset of read English speech sample.
So there are a lot of users, there's a lot of speakers there that pronounce different texts, something like
yes.
this.
Yes.
So this is an analog of ImageNet or Wikipedia for the image and text domains. Is it true?
So please reload.
So this is the image, this is a data set that can be interpreted as some analog of ImageNet or Wikipedia for image domain and text domain, but for the case of speech domain.
No, I think it's not massive. It's a famous data set, and in all tasks of audio with speech processing, the authors performed experiments on the LibreSpeech, but it's not so massive like ImageNet, as I know.
Okay, and one more question. We all know the image in painting problem. And it seems like the architecture that you have presented can be used for image in painting as well. So you just use a UNet-like encoder-decoder architecture and then some CNN for calculating the loss. So if we instead try to solve the image in painting problem with this type of architecture, we also would get a success. Or there are some specifics inside the architecture, particularly designed for speech processing.
No, I think that there is no specific, so we can feature a structure that, of course, based on VGG 16, of course, we can apply this framework to images. And the other architectures UNet, we also can apply to images, and there are possible that if we try to use this architecture on image in painting tasks, we can get not bad results. And I think that this architecture was the authors this architecture was taken from image in painting tasks originally.
Yeah, inspired by that architectures. Any more questions for this presentation? Okay, if not, then let's move to the next speaker. Evgenia Miluta, please proceed.
Okay, is it clear? Do you see the screen and me?
Yes.
Okay, let's start. I chose the topic with such, I chose the article with such theme because I think that's a very popular theme nowadays. And it connects with deep learning, as could see from the name of the article. So the main aim of the author was to investigate the novel problem of predicting teachers' ratings in online education platforms based on online educational materials. There was 2 tasks, the instructor rating and course rating. Author used subtitles of online courses on Coursera and take such statistics from it. Each course had any sections, and in each section some lectures. Okay, while they make a model, they find out 2 challenges. The first, that it's necessary to somehow implement model with using the student-teacher interaction, and using course structure for, and they think that it was important thing in constructing models. The structure, there is an example of structure, of course. Okay. At the first, they find out some features from the course. You could read it, and plus or minus, that means the positive or negative correlation between rating and such feature. They use these features, they add these features later to the main data set, and now let's continue. The data set presented as the next parameters. The first is lecture course subtitles for each lectures, then section index, lecture position index, and additional features as presented below, and ground truth label. So at the first, as I said, there is a limitation of BERT model. They can use only 500 tokens, but the mean length of if lecture was over the 1000, but they, as I understand, they take only first 500. Then they add CLS token to each lecture and do the forward pass during to the retained BERT. After that, they take this CLS embedding and add to it embeddings of lecture position and section position. Then they add to such zetas for each lectures. They add CLS tokens, zeta 0, which take all the information from each section of the course during to passing from pass it to transformers, and they use the linear transformer as which was discussed in the lecture on the previous lectures. They pass it to multi-head attention, and then do the layer norm and feed-forward network, and pass through feed-forward network. And then they concatenate it with extracted course features and pass it to the linear layer like this. But it's the main proposed model. Besides, they do some experiments with more with less complex models. They take for train 17% of all data set. Validation is 9, and 20% for test. And to use the simple Messier metrics. There is some parameters of their experiments shown. And they take such results. For the first, they use only features, they extract only coarse features and make a linear regression, SVM, multi-layer perceptron, random forest, data boost, gradient boosting, and Baggins 7 models only on these features. As they said, maybe these features was достаточно. I can't remember how to translate.
Enough.
Is enough, sorry. Then they add the word vectors for each of each lectures. And there's some decreasing in RMSE and Maya for each task. And then add the doc2ec of each course, as I remember, plus extracted course features. At the end, they make a baseline for BERT. Now let's see how they take it. At the first, they take only lectures without features, and do all the things like this, like on the scheme, as was shown below. Then they said that maybe our structure is not important, and take only CLS embeddings after BERT, pass it through transformers and linear layer. And then they use only BERT embeddings, CLS, which pass to linear. So in this lecture BERT, they didn't use this course structure, as they said. And the next results shows that when we do such a transformation, as was shown below, we had such results. So I think it's proposed and the three models of below. And we see that proposed model, as I described, which I described at the start of my presentation, gets less Maya and RMSE metrics. And these results are statistically significant. So they do the next findings, they do the next conclusions, that the extracted coarse features they add to the model some quality that we must use these features. Coarse structure information is also necessary, and the global transformers, which gets us the how to say, gets us also exchange between lectures and sections, is also necessary for such kind of models. So in the future work, they think that it could be the multimodal features, for example, taken from the audio or visual set, that could be extracted and have to more robust model. Thank you for your attention. Any questions?
Thank you. Well, very interesting. So once again, what the particular information is used as input to the model from the course? What is this? Lecture titles, text description of lectures, what?
Okay. For the course features, they used the lecture titles. How it used? It used to construct some graphs and calculate models. Models, yes. or maybe modularity of each lecture, and it was like a feature. But for the BERT, they used only subtitles. These features was used as extracted course features. That's the question ratio. That's the ratio of questions in the whole pool of the in the sentences of lecture. Emotion appealing. That's the emotion entropy. They find out 8 emotions which could increase the students' studying quality, and they think the more such emotions in the lecture, the more interesting course, and the more qualitatively or quantitatively качественный.
Qualitative.
Qualitative course will be. And
so this is extracted from audio or from text?
From text. They use only texts, subtitles for each lecture. On Coursera, maybe you know that there is for each lecture subtitles. We have for each lecture subtitles. And they, as I understand, they take the subtitles by themselves from the site, and using these subtitles, субтитры, правильно я перевожу? Может быть, я это неправильно перевожу?
Yeah. That's correct.
Correct, yeah. And after using this, and from these subtitles, they find these features.
Okay. And did they try to analyze their results to say what particular features of the course make this course bad or good?
Yes, there is an results of set. If I clearly understand your questions, they at the first they make a correlation analysis for find out is there some correlation between ratings and such kind of features, and plus in brackets that's a positive correlation, the statistical significant positive correlations, and minus that negative correlation, significant negative correlation between ratings, as for instructor ratings, and course ratings. Sorry for my English.
Well, according to this feature, I understand that our course was not very good because you have a low question ratio. We have a lot of basically generalists and words like this. So it seemed that your rating would be not very good for this course.
Question ratio, it's question from the teacher, not from students. As they said that if a teacher states the questions correctly and the type of questions also have impact on the course rating, the instructor rating.
Okay, any more questions?
I have a question. Is there any experiment or something like that that shows how you need to change the course so your rating would be better?
Okay, I had the same question while reading the article, but authors only said that it could how to say promote. It will help teachers to prepare their course more maybe clearly. Maybe they want to say you must how to say записать make a subtitles maybe for your course, and then pass it through the model and take the some rating for your course. But they don't say how exactly you must change. So I had the same question, but there is no answer for it.
Okay, any more questions? If no, thank you. And let's make a 10 minutes break to relax a bit and continue in 10 minutes. Please. We don't hear you. Please turn on your mic.
Hello?
Yeah.
Can you see my screen?
Yes.
Okay. Hello, my name is Dmitry Lukov, and I'm going to tell you about article Transferring GANs, Generating Images from Limited Data. Transferring knowledge of pre-trained networks to new domains using fine-tuning is a widely used practice in discriminative models. It has become the default approach for many applications with limited training data or slow conversions. But what about generative case? How we can apply fine-tuning for generative adversarial networks? Authors of this paper studied domain adaptation for generative deep network. Generative adversarial networks can generate samples from complex image distribution. They consist of two networks, a discriminator, which aims to separate real images from generated images, and a generator, which is optimized to generate images which are classified as real by discriminator. The theory was later extended to the case of conditional GANs, where the generative process uses a conditional prior, which is provided as an additional input. At first, let's consider the problem of evaluation GANs. It is quite difficult, and there is no clear agreed reference metric yet. In general, a good metric should measure both the quality and diversity of generated data. Diversity is important because in worst case, generator can always return some constant value which is recognized by discriminator with good score. The authors consider two metrics. The first one is Fréchet inception distance. It is actually a Fréchet distance in embedding space, where embedding is computed using inception model up to some specific layer. Here, He1 is the full data set of real images, and He2 is generated samples. The second one is independent Wasserstein critic. D hat here is a network with clipped whites trained to produce high values at real samples and low values at generated samples. Let's take a look at implementation details. In this paper was used improved version of Wasserstein GAN with ResNet in both generator and discriminator. Output images have size 64 times 64 pixels, and they used Adam optimizer with learning rate 10 in power -4 up to 50,000 iterations. Target dataset is Elsan bedrooms. Here we can see samples from this dataset. The network of the GAN can be initialized with either random or pre-trained weights. In the first experiment, they consider all possible combinations of using a network pre-trained with ImageNet or training from scratch. Here we can see interesting result that transferring discriminator is more critical than transferring generator. Using pre-trained generator without pre-trained discriminator is even worse than GAN without transferring at all. But the best result is reached with using pre-trained weights for both networks. Here we can see evolution of evaluation metrics. As you can see, pre-trained network can reach given score in significantly fewer iterations. And even after reaching plateau, there is some gap between metric values. In the next experiment, authors studied how using pre-trained network can decrease required dataset size. This table shows evaluation metrics measured for different amounts of training samples of the target domain. GAN adapted from pre-trained model requires roughly between 2 and 5 times less images to obtain a similar score than a GAN trained from scratch. At this figure, we can see images generated at different iterations. Pre-trained network can generate high-quality images already in earlier iterations. They have more sharp edges and more realistic details. In conclusion, I can say that using knowledge from pre-trained networks can shorten the convergence time and significantly improve the quality of the generated images, especially when target data is limited. That's all. Thank you for your attention.
Okay, thank you. I have a question. You said that this bedroom data set has size 64 by 64. So how they transform ImageNet pre-trained network to this different sized data set?
So 64 times 64 is the output of their network.
Yeah, but you say, for example, that you transfer a discriminator. So you take a discriminator first trained on ImageNet, yes, and then you try to use this discriminator within a GN model for bedroom dataset. And for bedroom dataset, you have a different size of the image. So how do you transfer? You upscale this image to the 224 by 224 or what?
Good question. They actually didn't say about that. I think it can be simple upscaling.
Okay, well, I would say that, well, this is too simple paper for discussion. So you just said that, well, if you have an ability to use some pre-trained network, please use it. Yes, but this is, well, this is always true for all kinds of problems that we solve, not particularly for generating with GANs, so on. Okay, any more questions to this for this presentation?
Yeah, can you show the diagrams for loss functions? Where it was, yeah, these ones. Is it a train or test loss?
Is it actually not loss functions? It is a special matrix, and it is validation set.
Okay. So my point is that seems like the red one, the pre-trained network, is not the does not have the form of the tail of the Scratch network. So what I want to say, does that mean that conversion by pre-training to the wrong minimum actually gives us the ability to converge then to a better minimum? Were any comments on that point in the paper?
Sorry, I didn't get the point.
I mean that they proceed the optimization and look like they flatlined, but they flatlined to different minimum. And that can be caused because at first the pre-trained network converged to some probably better defined flat minimum, because maybe the pre-training dataset was larger and it had better generalizing abilities, and then it converged to consecutive corresponding better generalizing local solution to the given problem to which it was transferred.
Yes, I think it is. It can be because of larger dataset size in pre-trained case.
Okay.
So network from Scratch can't reach the same metric value even after a big amount of iterations.
I guess they haven't researched on the flat minima or sharp minima of the obtained network. It is, well, it is a different research from a loss landscapes scenario. I guess that they haven't analyzed their results from that perspective.
No, I was just speculating. My question was whether the Scratch network can reach the same performance as a pre-trained network, or that pre-training dataset was essential for reaching this minimum.
Well, we don't know. Well, so if you just increase the number of iterations, you are not able to reach the same metrics. So you should do something additional in order to achieve such result.
Okay.
Okay, thank you. Let's move to the next speaker, Andrei Ostapov.
Thank you.
Okay, do you hear me?
Yeah.
Can you see the screen?
Yes.
Oops. Hello. Today I will tell you about AutoDeepLab, a hierarchical neural architecture search for semantic image segmentation. Let's start from describing the major part of algorithms and architectures which are used for segmentation. They can be described as encoder-decoder approach, and such networks consist of two parts. The encoder, which takes an RGB image as an input and produces n feature maps of different spatial resolutions. And the next is decoder, which takes n feature maps from encoder as an input, merge them into one with the original resolution, and makes final segmentation prediction. Another popular approach is stacked Hourglass architecture. The basic idea is simple. Let's just make a sequential execution of some unit-like autoencoders. And each autoencoder at the final stage tries to predict final segmentation. So final loss is a weighted sum of losses calculated from predictions from all autoencoders. Such architecture proved to be effective on such tasks like segmentation of human body into parts and estimation of human pose and others. So there are a lot of different architectures, and iteratively looking for the best of them is a time-consuming work. So the authors of the paper provide an approach called AutoDeepLab, in which they solve tasks of automatic neural architecture search. So AutoDeepLab is AutoML algorithm. As you can see, the major part of segmentation architectures have some similarities, like the spatial resolution of the next layer is either twice larger or twice smaller, or has the same spatial resolution as the current layer. And in most of architectures, the smallest spatial resolution is the original, which is downsampled by 32. So the authors took these two ideas and provided such base architecture, which consists of some layers, which are set in two-dimensional grid. So on each row we have L capital layers, and in each column we have 4 layers which correspond to different spatial resolutions. So such idea can lead to can learn different types of architectures. For example, it can learn something like convolution-deconvolution architecture, or even it can learn something like stacked Hourglass. But in fact, this approach can't learn such thing like skip connections between encoder and decoder in such networks. Okay, how even this algorithm can learn an architecture? First of all, let inp from L and D and out from L and D be the input and the output of layer L with downsample level D. And input of the layer from the next column with downsample level D depends on three previous layers which have output feature maps with the same resolution, with twice higher resolution and twice lower resolution. So an input of current layer is a weighted sum of outputs from three previous layers with weights called beta 1, beta 2, and beta 3. There are some borders. I mean, the sum of there are some restrictions. Yes, the sum of betas must be always 1, and each of beta must be higher than 0. So the learning process always alternates between learning weights in each layer, while all betas are freezed. And the other step is learning betas while internal weights of layers are freezed. So using such iterative algorithm, architecture learns both internal weights of layers and betas. So the final architecture is searched as a pass from an input to the output layer as with a maximum cumulative sum over betas. So this is it. And the authors provide some experiments on some data sets like cityscapes, for example. And their architecture shows some good results which are competitive with some state-of-the-art approaches like PSP.NET and DeepLab 3+. That is all.
Okay,
one
thank
question.
you. Yeah.
Okay.
The previous slide, could you show?
Okay.
You said that we find the maximum cumulative sum of betas, yes?
Yes.
But I didn't understand. We have sum of betas 1, and how we find which sum must be maximum?
Do you see the cursor?
Yes.
Okay. Each layer has its own 3 betas for the upper layer, or for the same layer, and for the lower previous layer. While training, the architecture learns betas for each layer. And finally, when you want to subtract from a lot of layers from layer grid a sequential architecture, you just try all the existing paths from the beginning to the last layer column, and you just calculate the cumulative sum over the path for all the betas.
Okay, understand. Thanks. And the next questions I didn't hear. Maybe the layers from left to right, 1, 2 to the L big. Which kind of layers it must be? Convolutional or what?
Yes, it's all convolutional layers. Actually, the authors make something more complex than one convolution, but I think in naive approach, even one convolution can make some reasonable results.
Thanks.
Okay, I have a question about beta learning. Do they use any sparsity aware methods here, or they just say that we just learn beta in a way so it can be non-sparse?
I didn't notice anything about sparse methods.
So they don't want to skip out some of the connection in this graph.
I mean, the final architecture skips everything except of sequential paths.
Yeah, but it seems like you may have, if you do not learn your betas in a sparsity aware way, you may have a sufficient degradation when you, after the learning, if you just take the path which maximizes the sum of the betas, because during the learning, each layer have learned in such a way that it may use information from 3 previous nodes. But if you just keep them out, you may sufficiently degrade in
performance.
Did they comment on this? They made the final fine-tuning of the network, or how, or what?
I didn't see information about that. All they told is just training and finally subtracting the final architecture. I didn't see any information about fine-tuning, so I think they didn't try it.
Okay, understood. And what about the training time, comparing to learning just one model?
I think it's bigger, but they didn't provide time comparison with simple methods, but they provided some time comparison or learning time comparison with other AutoML approaches which exist for classification tasks. And for example, the AutoDeepLab learns 3 days on cityscapes, which is not that much, I think. And non-gradient AutoML approaches on classification tasks were learning more than 100 days, I thought.
100 days? You sure?
Actually, I'm not sure. I can recheck, but information looked. It looked like the performance was better, like 100 of times than the other approaches.
Okay, thank you. Let's switch to the next presentation by Lev Smirnov.
Yes, 1 second. Are you hear me?
Yeah.
All right. You see slide?
Yes.
Hello, I'm Smirnov Lev, and today I will tell about neural supersampling. A little introduction. Supersampling, it is a special anti-aliasing method. It is a method used to remove aliasing, jagged, and pixelated edges from images. Aliasing occurs because, unlike real-world objects, which have continuous smooth curves and lines, a computer screen shows the viewers a large number of small squares. These pixels all have the same size, and each one has a single color. A line can only be shown as a collection of pixels, and therefore appears jagged unless it is perfectly horizontal or vertical. The aim of supersampling is to reduce this effect. Color samples are taken several instances inside the pixels, not just at the center as normal, and an average color values is calculated. This achieved by rendering the image at a much higher resolution than the one being displayed. Then freaking it to the described size using the extra pixels for calculation. The result is a downsampling image with smoothed translation from one line of pixels to another, the edge of objects. The number of samples determines the quality of the output. Next slide. In the real-time rendering, each pixel is a point sample of the underlying high-resolution image, and then multi-sample anti-aliasing is disabled. As illustrated in the figure on the previous slide, there a dot at the center of each pixel represents the sample to render. Post-upsampling from such input is anti-aliasing and interpolation problem. In contrast to the blurring problems as the camera images super resolution application. And the challenge of high fidelity upsampling for rendered content is that the input images with point sampled pixels are extremely aliased at shading and geometry edges, and the information at the target to be interpolated pixels is completely missing. Next slide. In rendering, a motion vectors point at an analytical compute screen space location. There are 3D point, three-dimensional point that is visible at the current frame would appear in the previous frame with the subpixel precision as shown in figure, who you see in the slide. While the render and motion vector provide candidate matching between pixels for low cost, it presents a few limitations that prevent its direct use in multi-frame upsampling. First, because it maps pixel backward, as illustrated in figure, pixel at a previous frame cannot be directly projected to the current frame. Second, it does not consider dynamic disocclusion between the current and previous frame. That means three-dimensional points visible at current frame might to be occluded in the previous frames due to viewpointing change or object movement. An example in case is illustrated in figure. Third, in provides only a partial optical flow. This means only the motion of surface point and camera, and does not consider the change in lighting, shadow, view depend, reflectance, etc. This method applies the frame warping at the target high resolution space rather than the input low resolution. Next slide. In this slide, you can see architecture we state this paper. Let's analyze all this stage by one. First, feature extraction. The feature extraction model contains a three-layer convolution neural network. This subnetwork processes each input frame individually and share weights across all frames except for the current frame. For each frame, the subnetwork takes color and depth as input, who you will see in previous slides. This subnetwork generates 8 channels, learned features, which are then concatenate with the input colors and depths, resulting in 12 channels feature in total. The network details are given in feature in grid. Next, temporal projection. To reduce the required receptive field and whose complexity of reconstruction network, we apply temporal reprojection to project pixel samples and learn features of each previous frame to the current by using the render motion vector in order to fully exploit the subpixel backward motion vector. We conduct the temporal reprojection and the target high resolution space. First, we project the pixel samples from input low resolution space to the high resolution space by zero upsampling. This means assign each input pixels to its corresponding pixels at high resolution and leaving all the missing pixels around its as zeros. Zero subsampling is chosen for its efficiently and because it provides the network information on which samples are valid or invalid. Then we resize the render low resolution map of motion vectors to high resolution simply by bilinear upsampling, taking advantage of the fact sorry or advantages of the fact that the motion vectors are piecewise smooth. While such simple upsampling introduce errors to the upsampling maps at discounted regions, it will recovers the majority of regions compared to ground truth. Next, we apply backward warping of the zero upsampling previous frames using the sampling motion vectors, while bilinear interpolation is adopted during warping. In figure, we show an example of zero upsampling and warped frame. Note that the motion vector are only defined for an gens pair of frames. Future weight. The rendered motion vectors do not reflect dynamic disocclusion or shading change between frames. Thus, the warped frame would contain artificial sum such as ghosting at disocclusion region and mismatch pixels at inconsistent shading region. To address this problem, we introduce a feature reweight model to be able mask out this mismatch sample. The feature weight model is a free layers convolution neural network, which takes the RGB of the zero upsampling current frames as well as the zero upsampling warp of previous frame as input, and generates a pixel-wise weight map for each previous frame. With values between 0 and 10. With 10, the 10 is a hyperparameter. The reason we feed only RGB instead on the whole 12 channels features into the order-weight network, to further reduce the network complexity. Reconstruction. Finally, the future of the current frame and the weight future of previous frame are concatenated and feed into the reconstruction network, which outputs the recovered high-resolution image of current frame. In this paper, adopt a Freescale 10 layers UNet with skip connection for the reconstruction subnetwork. The network details in the blue figure. On this slide, you can see the result of the algorithm. Thank you for your attention. That's all.
Okay, thank you. Any questions?
No questions.
What about the speed of the algorithm of the test phase? Is it real time or not?
Real time. You can see speed on table right corner, table 1. Runtime MS for 4x4 upsampling. In resolution, you can see the speed with algorithm.
So all these warping methods inside they work really fast.
Yes, it is a real-time method. Yes, in a real-time method who work 30 FPS, 16 FPS by 11 milliseconds. Yes, 16 FPS.
Okay. Okay, thank you. Everything was very clear. Let's move to the next speaker, Alexey Gorbanosov.
Okay, can you hear me?
Hear, yes, but do not see.
Yeah. How to show this? Yeah. So.
Can you turn on your web camera?
Unfortunately, I don't have one. I have a stationary PC. I'm very sorry, but I don't have one. So my name is Gorbanosov Alexey. I'm from group 622, and I will tell you about compositional neural scene representations for shading inference. So what is the purpose of this paper? While rendering complex scenes, we have a lot of complicated effects going on in every scene. For example, ambient occlusion, color bleeds, global illumination, and many other parts, which are extremely hard to replicate. And computer graphics algorithms that capture these effects are usually working in offline modes rather than in real-time ones, because it's too complicated to integrate the whole scene to get this indirect illumination and all of this things for high quality rendering. This is an example of a classic approach of path tracing to rendering quite simple scenes, but with high quality results. And as you can see, they take up to 400 seconds to render this quite simple scene with the boxes, which is definitely not a real-time approach. So the purpose of this paper is to create a neural reshading algorithm that would take in the geometric information about the scene and compute the most complex effects for us in a smaller amount of time, maybe approximating them with a lower quality, but still saving us a lot of time. How does it work? So first of all, it takes in the observations of the scene. This is basically our training set. It consists of colored images, camera information, and different geometrical and material information that is baked into textures. Then it encodes it with a specialized neural encoder into neural scene representation, which captures the lighting, geometry, and materials information in it in a unified form. Why do we need the neural scene representation? Is because if several objects are out of the current shot and we don't have any information on screen about them, we still have to know about them because they can cast shadows inside of this shot, or for example, can cause color bleeds. So this is very important. Then after encoding, we get the neural scene representation, and to predict the final lighting, we compute the G buffer, which is basically the geometric data about the current shot, and pass it to some image generation algorithm. In current paper, they use either UNet or Pixel network to generate the image, and we get the final result. One of the most important innovations here is the partition system. So we divide the scene representation into 3 partitions. Here we can see the attributions. The red attribution is to the material partition of the scene, the blue one to the geometric, and yellow one to the lighting one. It helps us debug and trace the problems with the rendering approach and see why certain artifacts keep appearing in our neural reshade. Because one of the biggest problems right now with the neural approaches to reshading is that they perform as a black box, and we have no idea why they have certain artifacts or they don't. So this partitioning helps with it. So yeah, that's basically a neural scene representation here. Its attribution to various parts. If we would look at different parts of the scene, for example, we can see that different parts of it require more information from different partitions. For example, the floor, the green part, is requiring more lighting information and geometric information because it must compute lighting, of course. And the most important part is that it has to compute the shadows. And computing shadows requires geometric information, while it doesn't require the red part, which is the material information, because the whole floor is white and it basically doesn't need too much information to determine this. While the wall, for example, it requires a lot of information about the material itself because it's a textured part. So we can reason about our rendering approach. Also, one of the biggest changes is that they introduce dynamic change of size change for partitions. So they make partitions trainable, partition sizes trainable. It's basically a tuple of sizes that is afterwards fed into a softmax operator, and we get the sizes of partitions so that we can utilize a fixed amount of space, but at the same time, focus on the most important partition. For example, at first stages, we usually need more lighting, while on the last stages of our training, we usually need more geometric information in order to predict better shadows, which are details of the image. So here we can see the partition dynamic size change while training. We can see that the lighting is peaking at first because lighting is the most convincing and the most kind of the most important part of the image. But at the end, for example, we have a peak of the geometric information, the blue line, which comes in to feed in the details of shadows, for example. Also, it allows for a great compression approach, because we can introduce the fourth partition, which is a null partition, which doesn't do anything. But using, if we would optimize, including some null partition, we would basically have a spare space that we can not use, for example. So if we include a beta, some kind of parameter that is inferring compression, we can increase the size of the null partition as much as we want. We would lose in quality. As you can see, the teapot on the left picture is of different color to the right one because of the compression, but still the image looks quite convincing. Also, choosing a generator in this talk is quite a complicated task, because UNet gives generally better results concerning different effects, except for shadows. For example, here we can see that out of view shadows are not captured by UNet, while being captured by Pixel. The way they approach this problem to make them work with UNet is they introduce an auxiliary generator, which is black and white, and it only generates shadows, and then this shadow results are fed inside of a UNet architecture, which finally gives a convincing result. So yeah, these are 3 results with pixel generator and augmented UNet generate and reference. And finally, the results. So here, the 2 right columns represent the ground truth and the generated image. As we can see, they are really close. The only thing that is evidently different is the reflection in the mirror. And the difference in generating these images is extremely huge. Reference image took 25 minutes using the path tracing method, while the neural method took about 400 milliseconds. So it really saves time. And some more results here. It also is this method is also capable of introducing reshading to the scene. For example, we can interpolate between different shadings of the scene in real time. So here we can see that there is a scene, and just by toggling between different scene representations that we have, we can dynamically change the shading of the scene, inferring like very smooth interpolation between different shading conditions that might be happening there. So that's it. Thanks for listening.
Okay, thank you. I have a question on what particular information is used for training the network. Just some particular frames from a particular scene, or what?
Yes, we have they've had a scene which is called Simple Room, this one. And what they do is that they generate a lot of different shots, random shots from this scene. As about, I think about 150,000 shots from different angles with all of the needed information. So, and that's it.
And so they learn from this 100 frames the neural network and then, well, generate this scene in all other angles. Yes?
I think that they learn it from 150,000 angles that they've had, and then they do something like the same amount of angles to
Okay, and what about transferring between different scenes? Is it possible to learn on one scene with the same set of materials, similar set of objects, and use it for generating something for a different scene, but with the same type of objects?
I would say yes, because this is something that they do in here. So this is the same scene. It contains the same exact geometric information, so it's the same sphere, but they change the materials and lighting conditions. So, and then they interpolate between them. So it's kind of, that's, I think this is exactly the same thing. If we would try to change the geometric information, then probably it wouldn't work, because we would get shadow artifacts and things like that, because the algorithm would learn about the objects which are not really there at this time.
Mm-hmm. Okay. Any more questions to the presenter?
Yes. Can you comment on the partition dynamics? Is it happening during the training process? Or
yes,
the generation?
Yes, it's happening during the training process. So these are just trainable parameters, basically. These are the graphs that show the percentage each partition takes during a particular step in training. So there is like 1 million steps, and it kind of progresses this way. Because
and how many? Yeah. Okay. How many epochs does it usually take to learn the good representation?
That's a really good question, because I don't remember. I would guess that it's not 1 million, but I would say that it's training about 9 days. So I think it's quite a lot.
9 days for one scene?
Yes.
Oh, interesting. So not an online algorithm.
No, you can train it. Theoretically, you can train it for every single scene you have, and then like use it in online mode. It takes a lot of pre-computation, but generally it's working in real time for static scenes. I should mention that it's also very limited in a way that it works only on indoors, quite simple scenes right now.
And about the generator, it's a symbol for path network. It's not some kind of recurrent network or
no. It's it's a simple one.
So predicting is very simple.
Yes, it's straightforward, pretty much.
Okay, thank you.
Okay, any more questions? If no, thank you, and let's move to the next speaker, Svetlana Kryzhanovskaya. Please proceed.
So, okay, hello everyone. Do you see my slides?
Yeah.
Okay. My name is Svetlana Kryzhanovskaya, and today I want to tell about unsupervised cross-lingual representation learning, especially about XLMR model. Some motivation for cross-lingual learning. It is known that pre-trained BERT model can be fine-tuned with just one additional output layer to create state-of-the-art models for a wide range of different tasks, such as question answering, language inference, and other without substantial task-specific architecture modifications. And the idea is to extend this approach to multiple languages. And here comes XLMR model. So XLMR stands for RoBERTa-based cross-lingual model architecture. And it is a transformer-based multilingual masked language model that pre-trained on text in 100 languages, which and it is obtains state-of-the-art performance on cross-lingual classification, sequence labeling, and question answering tasks. What are the problems of the previous models? All previous cross-lingual models, such as multilingual BERT or XLM, that are all transformer-based models, were pre-trained on Wikipedia, which provides a relatively limited scale, especially for lower resource languages. What is more, there is a curse of multilinguality. That means that more languages leads to better cross-lingual performance on lower resource languages up until a point, after which the overall performance on monolingual and cross-lingual benchmarks degrades. And what is more, a single large model for all languages degrades per language performance. And if we want to evaluate model on one language, it could be better to learn one monolingual model, but we want our multilingual model to save performance for per language tasks. The evaluation of cross-lingual models is closely connected with cross-lingual understanding, which is a field that concerned with learning models on data in one language and applying it to other languages. And much of the work in cross-lingual understanding focuses on the zero-shot setting, which assumes that labeled data is available in one source language, usually it is English, and not in any of the target languages in which the model is evaluated. And little reminder about BERT model and its descendant RoBERTa. So BERT is a pre-training model that is used to learn a latent representation of the input text, and its state-of-the-art performance is based on two things. First, it is novel pre-training tasks called masked language model and next sentence prediction. Oh, I'm sorry. So the next sentence prediction task allows BERT to learn relationships between sentences by predicting if the next sentence in a pair is the true next or not. So RoBERTa is an improvement over BERT. RoBERTa removes the next sentence prediction task from BERT's pre-training and introduces dynamic masking, so that the masked token changes during the training epochs. And also, RoBERTa uses much more text data for pre-training, and these improvements allow this model to achieve better performance than BERT. And now let's talk about the XLMR model, and let's start with the data that is used for training. XLMR is trained on 2.5 terabytes of text data on 100 different languages. And the data set is called Common Crawl. And the figure shows the difference in size between the Wikipedia corpus that is used by previous models and the Common Crawl corpus that is used for training XLMR. And it is much better because Wikipedia are too small and it doesn't enable unsupervised representation learning.
I just turn off my notification. And now let's talk about some details of XLMR model. It is a Roberta-based model with two architectures, differs on the number of parameters. And for training, they used the multilingual vocabulary of 250,000 tokens with a full softmax and mask language model for training. Batches from different languages are sampled according to a multinomial distribution proportionally to the sizes of language subsets. And let's go to the evaluation. There are several benchmarks that are considered for cross-lingual evaluation. There are natural language inference, named entity recognition, question answering, but I will talk only about natural language inference task. It is a task of determining whether a one sentence or hypothesis is true, false, or undetermined given in another sentence. And the XNLI dataset comes with ground truth validation and test sets in 15 languages and the ground truth English training set. And also there are several evaluation approaches. The first approach is zero-shot setting, when we use only English training set and evaluate our model on validation and test sets on other languages. The second approach is translate test, when we translate all validation and test sets to English and use only one English model. The third approach is translate train, when the English training set is meshed and translated to each language, and a multilingual model is fine-tuned on each training set. And the last approach is translate train all, when we use a multilingual model, which is fine-tuned on the concatenation of all training sets from the previous approach, or translate train. And here we can see the results of some experiments on understanding multilingual masked language models. And when reporting results on high resource languages, we refer to the average of English and French results. And when we talk about low resource languages, we talk about the average of two rare languages that is called Urdu and Swahili. And we can see that all models trained on Common Crawl dataset obtains significantly better performance than ones that trained on Wikipedia. Also, we can see that adding capacity, that means increasing hidden sizes of the hidden representations. And this allows models to overcome the curse of multilinguality. And also another fact that scaling the size of the shared vocabulary can improve the performance of multilingual models. And here we can see the overall results on the XNLI cross-lingual classification task. And we can see that XLMR sets a new state-of-the-art performance on this dataset. XLMR, so we can see that XLMR obtains 80.9% of accuracy, outperforming the previous models. And using the multilingual training translate train all approach, it further improves performance and reaches 83.6 accuracy. And it is a new state of the art for this task. Another goal of multilingual model is to obtain a strong performance on tasks for each language. So we can prove this ability by evaluating Exclamar model on the GLUE benchmark. It is a set of classification tasks for evaluation the English performance. However, we can see that monolingual Roberta model outperforms Exclamar, but only on 1% on average. That's all. In conclusion, we can say that Exclamar provides strong gains over previous multilingual models on different tasks, such as classification, sequence labeling, and question answering. It is also shows strong improvements on lower resource languages, and also the results demonstrate the possibility of learning one model for many languages while showing strong performance on one language tasks too. That's all. Thank you.
Okay, thank you. Well, I have a question about this multi-language vocabulary. What is it? Is it just a concatenation of vocabularies from separate languages, or there are words that are the same in different languages?
Actually, there are sentence piece models, so we have tokens that are the same for different languages, and the vocabulary is built for the concatenation of the subsets for different languages.
So these are not words, but parts of the words?
Yes.
Okay, and why? So why in this CC data set, Russian language has the second place? It seems like it should be Chinese or Spanish.
So there are a lot of data for Russian language. I don't know why actually, but it is popular language.
So do they have a Chinese language here, or any Asian language?
Yes, of course. There are. Yes, but we can't see them on this figure just because we want to show the amount of low resource languages amounts. So there are, of course, French, Spanish, and other European languages too.
Well, my question is about, it seems like with this multi-language vocabulary idea, they are more concentrating on languages that have the same letters, the Latin languages, because uniting Latin languages is easier for their model than uniting languages of different vocabulary. So that is why my question: do they have Asian type languages or other non-Latin type languages?
Yes, of course. There are 100 different languages, and of course there are not the same like all European languages.
Okay. Any more questions? If no, then thank you. And let's move to the last talk for today by Alexander Chernyshov.
Hello, do you hear me?
Yeah.
Okay, great. One moment, please. So now you should see my presentation.
Yeah, we see.
Okay, so let's start. Hello, my name is Alexander Chernyshov. I'm studying in group 517, and today I will talk about EfficientNet. It's a recent paper. It was published in the previous year, if I'm not mistaken, by Google. And it's interesting paper which says us how we can scale up neural networks, convolutional neural networks, in efficient way. So let's remind how we can scale up convolutional neural networks. Usually there are three different ways. We can make them wider. It means that we increase the number of convolutional filters in each layer. Or we can make them deeper. It means that we stack more layers. Or we can train these neural networks on images with higher resolution. And these are three common ways. And we can see that they show the efficiency. If we, for example, stack more layers, it's the second picture, we get the neural network with high accuracy. And it's the same for width and resolution too. So if we increase width of neural network or resolution for input images, we get more accurate neural networks. But also we can see that accuracy gain quickly saturate after reaching about 80% of accuracy. And so, okay, of course we can stack more layers, or we can make layers wider in neural network, but we will get a little profit from that. And so such neural networks will be expensive to maintain. And so we need more efficient ways to scale up neural networks. And so the authors of this paper proposed new such method. So the idea is very simple. Let's scale up not only one dimension, depth, width, or resolution of images. Let's scale up all three dimensions at the same time. And intuitively, the compound, this method, which they propose, makes sense because if the input image is bigger, then the network needs more layers to increase the receptive field and more channels to capture more fine-grained patterns on the big image. So this method is intuitively good. And so let's talk about it in details because there are some problems which should be solved. So let's represent a convolutional network as a stack of layers. So F1, F2, etc. are layers here, and X1 is an input image. We can rewrite it in such compact form. And also we know that real convolutional neural networks have special structure. Some layers in there are repeated. And so we can rewrite a neural network in the following way, in the second line. Here, fi to the power of li means that layer fi is repeated li times. And that's it. And what the others propose? They want bring fixed fi layers, and they want to change li, hi, wi, and cy parameters to get more efficient and more accurate neural networks than if we change only one of these parameters. Okay, And we can see that Li, Hi, Wi, and Cy parameters, there are 4 times S such parameters here. And so it's not easy task to choose the perfect parameters, because there is a big amount of parameters. And so it was proposed to restrict that all layers must be scaled uniformly with concentration. So that's mean that, for example, let's we have Fi, Li, Hi, Wi, and Cy with heads. It's some predefined parameters in baseline network. And we will get new networks by multiplying these predefined parameters by some scale factors. D corresponds for depth, R corresponds for resolution, and W corresponds for width. And so we can see here that we have here new network with more layers, with images with high resolution, and more wide layers. And so, okay, we want to choose such network. We want to choose bigger network, and we want to maximize accuracy for it. And also we have some real life constraints. We have a constraint on memory of this neural network. And also we have a constraint of inference or training time for this network. FLOPS here stands for floating operations of neural network. So it's a number of operations which are performed when we pass one image through the network. Okay, and so our task to choose perfect D, R, and W parameters. Here we can see for different D and R parameters and for different W parameters. So there are points of the same color, but points of the same color differs only by W factor. And so we can see that the bigger factors are, the better accuracy we get. And also we can see that it's profitable to change all the parameters simultaneously. And so that's why this method should work. Okay, and there is the last piece of puzzle. It's how to choose D, W, and R parameters. Let it be, it's just an alpha, beta, and gamma to the 5th power. And we have here a constraint, alpha times beta squared times gamma squared is approximately equal to 2. It have the following sense. If we count the complexity of convolutional layer, we can see that it's proportional to the depth of neural network. It's proportional to the width squared of neural network and resolution squared of network. And so we can here to have that if phi is equal to 1, then our running time of neural network increases by 2 times. And so the phi means how slower our network will be. Okay, that is choose architecture of neural network by some method. They not so efficient NetBinOL was developed by leveraging a multi-objective neural architecture search that optimizes both accuracy and flops. And here you can see its architecture. Bconf and bconf, it's just inverted residual block. It's used in MobileNet, for example. Okay, we constructed efficient.net B0, and we want to construct from this network. We want to scale it up, and so we fix phi equal to 1, and then we choose alpha, beta, and gamma. No, we're using grid search here, and we get such values of alpha, beta, and gamma. And then we fix them and change phi to obtain bigger neural networks. And so these neural networks will be slower, but they will be more efficient. And we can compare the results of efficient.net for different versions of efficient.net. They are grouped here by the accuracy. So in each group, accuracy is about to be equal. And we can see here that efficient.net is several times faster, and it has several times less parameters as other neural networks. Also, we can apply compound scaling method to some existing neural networks, for example, MobileNet or ResNet, and it also gave us better accuracy. Also, we can apply efficient.net on some transfer learning datasets, and that has got improvement on 5 out of 8 datasets that they have tested. And also, we can see for different scaled up neural networks the class activation map. And we can see that for compound scaling, we got the best class activation map. So it means that this neural network focus on more relevant regions on the images. So that's it.
Okay, thank you. I have a question about the type of data sets for which this idea works. Can we say that this works only for huge data sets like ImageNet or bigger, or we may use similar ideas to say NIST, and just with little upscaling or small model, we are still able to find the better networks?
So I didn't understand you when you talked about NIST. Can you repeat, please?
My question is about the type of the data set, the size of the data set for which this efficient.net actually works. Does it work only for big data sets like ImageNet and bigger data sets, or we may use a similar idea for small data sets like NIST, when we just, with efficient.net, we just make a little upscaling of even a small model and still able to find a better network? Do you hear me?
Yes, I hear you. Okay, no. Okay, we can use efficient.net on small data sets, but I didn't get what's the main point of your question. So will it work with small data sets? Or?
Yes.
No, okay, we, for example, the small version of efficient.net, B0, it's a small neural network, so it
B0 is small. It seems like it had 10 plus number of layers with 5 by 5 convolutions, something like this. That it is not quite small thing.
Okay. Yes.
Well, do you know that somebody have used EfficientNet for small data sets?
No, I didn't hear about such cases. But okay, it sounds for me that EfficientNet can work with small data sets.
You sure that we didn't get any overfitting with this upscaling?
No, of course we will get overfitting, but okay, yes. If we talk about overfitting, then it's not a good idea, because of course it has several millions of parameters, but the NIST is 60,000 objects, has 60,000 objects, and so of course it will fit. But as I understand, we just can train it not a long time. So we can train it a little, I think, and it can work with NIST maybe.
Not a long time comparing to other neural architecture search method that we've heard today, but 100 of days of learning. Yes, it seems like that this works a bit faster. Okay, thank you. Any more questions?
Maybe one question. Is there any principal difference between just take a different age, a high weight and other parameters, and or take D, W, and R parameters, or it's just more comfortable to evaluate and compute the model?
So what are you talking about?
I think that's the previous slide.
This one?
Okay, you said that we just multiply height by D, yes? Or
height by R. So R stands for resolution. So R is multiplied by H and W. H and W are the size of the image.
And just the RD, it's just more comfortable to calculate, yes?
Comfortable to what?
What I want to say, it's like we take different height, weight, and channels, yes? It's the same as we get the different height, weight, and channels, yes? Okay.
There is some problem of understanding from my side. So what are you talking about? You're talking about can we choose different L, H, W, and C, or what?
Why we take these new parameters, or not just take different H, W, C, and L?
Okay. Okay, it's possible way we can choose different L, H, W, and C, but as I said, there are too many such parameters. We can have there 4 times S such parameters, and it's a difficult task to find perfect neural architecture if we don't have any constraints. And so the idea of this article was to reduce the number of such parameters. And so now we want to choose, okay, we have now L, H, W, and C fixed, and we now can only vary D, R, and W. And so now we have to choose only three parameters.
Okay.
And then, yes, okay. And then there is some procedure which selects the perfect parameters in some sense.
Okay, and on the previous, where it was 3 graphics, there this comparison was, so when we take different W's, which D and R we take, optimal or equal 1?
Okay, here, no, okay, but for example, for the first graphic, the W over I is right, and D and R are equal to 1, yes. Okay. And it's the same for these 2 graphics, yes. And so these were just illustrations of that changing only one parameter for neural network is a good idea, but it's not a very efficient idea. Okay. So here we can see that changing several of parameters is a better idea.
Okay, any more questions?
Yeah, actually, the last question from me is the network itself trained? Because in the formula, I did see optimization over weights of the network only on hyperparameters.
So could you repeat this?
Yeah, can you change to the slide with the formula for method where we maximize over hyperparameters? Yeah, here.
This one.
Do we train the network, retrain the network for the hyperparameters, or we just reuse the old kernels from some baseline network?
No. So we have, okay, we choose some architecture for baseline model. Then we, using this baseline architecture, we construct B1 to B7 architectures, and then we train them separately. So,
okay.
So of course you should train them because they have different number of parameters. So you can't just add more parameters and do nothing. So of course it should be trained.
Okay, thank you.
Okay, if no more question, let's finish our today lesson. We are almost perfectly on time. So this was the last lesson within the course this semester, and next please prepare for the examination. I know that for you that the examination will be in English as well, so be ready for that. And what else? I don't know if you need a consultation, well, a day or two before the exam, please let me know and we arrange this thing. Okay, any questions?
Do we have
Is there any known date when the exam will be?
Yeah, for sure. The timetable is already known. Just a second, I will see.
It's January 11.
There are 2 dates for 2 groups. So for MMP group, it will be 11th of January. And for computer vision group, it would be what? 15th of January.
Я еще вопрос организационный задам, но после того, как на все остальные ответят. Там просто вопрос со мной связанный, а не с группой.
Хорошо.
А про формат можно тогда, если можно сейчас про это сказать?
Так, формат экзамена. Давайте, значит, мы вас всех заранее распределяем по времени сдачи. То есть там, не знаю, там Иванов там 11:00, Петров там 12:15 и так далее. Значит, вам за час до этого времени, значит, по почте придет письмо, в котором будет указан номер билета и ссылка на Zoom. Значит, я, видимо, буду ориентироваться на e-mail, которые у вас указаны в AnyTask. Значит, там где вот список группы. Соответственно, получив это письмо, вы в течение часа готовитесь сами самостоятельно, за вами никто не следит, то есть пишете ответ на билет. Потом вот ко времени подключаетесь по заданной этой Zoom-ссылке и индивидуально как бы с преподавателем 1 на 1 начинаете беседовать, значит, по билету и там по курсу. Вот. При этом, значит, мы от вас ждем, что вы обеспечите как бы условия для того, чтобы мы могли как бы эффективно формулами друг с другом общаться. То есть либо у вас есть планшет, и тогда вы как бы пишете на разделяемой доске в Zoom, либо, значит, вы берете как бы какую-нибудь любую выносную веб-камеру, допустим, мобильный телефон свой, да, ставите, чтобы она смотрела какую-нибудь на стопку книг, чтобы она смотрела сверху на стол, внизу бумажка, и на этой бумажке пишите формулы, чтобы преподаватель мог как бы оперативно спрашивать, напишите там формулу такую-то, вы сразу пишете, и мы все это видели. То есть вот как бы в таком режиме хотелось бы экзамен принимать. Ну и, значит, список вопросов к экзамену мы выложим, естественно, в ближайшее время. И как бы в этом списке вопросов там, как обычно, будет как бы 2 части. Ну, собственно, список вопросов и теоретический минимум. Такие как бы пункты по основным базовым понятиям из курса, типа там структура LSTM ячейки или что такое там трюк репараметризации. Вот. И предполагается, что на любой вопрос из термина вы как бы отвечаете с листа сходу. Говорите, а вот напиши мне, как LSTM ячейка выглядит, вы сразу пишете. Вот. И опрос по экзамену обычно как раз начинается с опроса по этому терминуму. Преподаватель тыкает какие-то случайные вопросы, вы отвечаете или не отвечаете. Ну, естественно, если вы не отвечаете на вопросы терминумума, то экзамен на этом, что называется, и заканчивается. Вот. Ну, вот как-то так.
А по длительности?
Ну, по длительности он, естественно, будет... Ну, мы на каждого выделим слот, я думаю, там, час или час 15, что-нибудь такое. Соответственно, вот за это время оценка за экзамен должна быть определена.
Есть ли какие-то критерии уже, как будут домашние задания вклад выносить?
Да, значит, формулу оценки мы пишем, то есть запишем, значит, ну, я думаю, что экзамен будет 30% от оценки, то есть 30% экзамен, 70% сумма за все задания, вот, плюс, значит, ну, там стандартные наши правила, что на финальную оценку 5, как бы, вы должны, решается не сделать одно задание. То есть, там, сколько у нас там всего заданий? Там 6, допустим. То, соответственно, на финальную оценку 5 нужно там не менее 5 заданий сдать на положительную оценку, на 4, соответственно, не менее 4, на 3 не менее 3. Вот. Ну, плюс, вот я говорю, по баллам должно получиться, исходя из того, что 70% это задание, 30% это экзамен.
Да, спасибо большое. То есть там на страничке курса еще потом появится, да, эта информация?
Да. Угу.
Спасибо.
Кстати, просрочка на день. Насколько снижает стоимость задания?
Так, значит, ну там мы из 10 баллов оцениваем, да? Значит...
Там вроде по какому-то даже заданию уже сразу сказали, что 0,3 снимается, у какого-то 0,5 было. Это так и остается или пересчитывают?
То есть разные снимались по разным заданиям?
Да, кажется, там...
Мне казалось, везде было 0,3.
Нет. Если разные, это мы точно как бы согласуем и, значит, пересчитаем вам баллы.
Ну, по стайл-трансферу было 0,3, кажется, если я не ошибаюсь. По конту 0,5.
Мне кажется, 0,3 разумная как бы цифра. Вот, давайте на ней остановимся.
А еще такой вопрос, может, не очень... Ну, в общем, когда примерно проверят задание? Есть какие-то сроки?
До экзамена. До экзамена все будет проверено.
Понятно.
Больше, к сожалению, обещать не могу. Я, конечно, как бы тыкаю палкой в проверяющих периодически, но как получится.
А вот жесткие дедлайны, это обычно было вот спустя неделю, да, после...
Да, спустя неделю после мягкого, да.
Угу. Да, понятно, спасибо.
А вот если задание сдано, но, допустим, за него мало баллов, это считается, что оно будет включаться вот в эти там, 6 заданий, 5 заданий, которые нужны для оценки?
Ну, как бы зависит от того, насколько мало баллов, да, то есть, условно говоря, если там по заданию из 10 баллов, там, не знаю, 1 балл поставлен, то есть, типа, там просто как бы большая часть заданий вообще не решалась, да, то есть, какое-нибудь только начало было решено, тогда, наверное, это не повод засчитать это выполненное задание. Но если по заданию хотя бы там 4 из 10 набрано, то значит, да, это считаем, что задание сдано на положительный.
Хорошо, спасибо.
Но мы это как бы уточним вот насчет, значит, ну, по тем оценкам, которые будут, какие задания как бы сданы на положительный балл, какие нет. То есть в этом смысле те задания, которые вы сдаете после жесткого дедлайна, мы, в принципе, тоже можем их принять. За них будет выставлено 0 баллов, но как бы это пойдет как бы вот в зачет, если кому-то не хватает количества выполненных заданий на нужную оценку, то таким образом можно вот этот норматив выполнить.
Хорошо, спасибо. А вот для подготовки, в принципе, лекций достаточно, да, будет? Или дополнительную литературу какую-то скинете еще?
Ну, смотрите, вообще как бы по этой теме, да, значит, литературой являются научные статьи, где там соответствующие методы описаны, и все. Никаких там книг, да, каких-то по дип-лернингу, в которых бы как-то полноценно и подробно описывались бы те там методы, которые мы сегодня обсуждали, ничего такого нет. Поэтому ну, вот у вас есть материал, во-первых, видеозаписи всех занятий, значит, во-вторых, вот ссылки там на где-то презентации, значит, мы выложили, плюс как вот там есть какой-то метод, не знаю, трансформер. Да? Самый вообще правильный способ значит, готовиться по этому материалу, открывайте статью про трансформеры, ее и читайте. То есть, это вот основной метод подготовки.
Кстати, жесткий дедлайн, он вообще так ли он необходим? Может, можно без него как-то обойтись?
Он необходим.
Да, но вроде не обговаривалось, что они будут.
Да, вот я согласен.
Ну, началось. Слушайте, вы как эти, как бы, вот как первый раз, да? То есть никогда до этого курсов не было, значит, никаких... У нас как бы все правила оценивания по всем курсам одни и те же, так что не надо тут...
Нет, Дмитрий Александрович, на ММРО уже... Ой, не ММРО, на праке уже жестких дедлайнов уже нету на 3-м курсе.
Да, Саня, это ты делал наверняка.
Называется, вот за вами стоило не последить, как бы, немножко, и уже, значит, что-то там случилось. Надо будет посмотреть, что вы там с формулой оценки изменили. Вот. Нет, значит, как бы сразу скажу, как бы на всякий случай, чтобы потом вопросов не было, то по всем следующим курсам, по которым я у вас буду вести занятия, в следующем семестре, через семестр, как бы, в этом смысле ничего не изменится. Такие же правила. Значит, мягкий дедлайн через неделю, жесткий по всем заданиям.
А баллы за выступление какие-то будут выставлены или как?
Да, я в Unitask проставлю.
А еще тогда такой вопрос, если расписание уже есть, а для второго экзамена по прикладным задачам есть дата уже?
Не, ну даты есть по всем. Вообще, честно говоря, странно. А что, оно не выложено на сайте факультета, описание экзаменационных сведений?
Да, я тут просто понял, нам прислали информацию буквально сегодня с утра.
Нам же в чат прислали ее, да, 11
народ
и 18.
Не в курсе практически все, что на самом деле уже известно.
Понятно. Нет, ну то есть расписание всех предметов известно. Значит, чего там? Прикладные задачи 18 числа экзамен. У вас вообще как бы суперкомфортная сессия. Всего 2 экзамена и как бы с большими паузами между ними. Так что есть время и задания там досдать, и подготовиться, и все.
А, кстати, например, на финальную оценку 5, я так понимаю, нужно еще экзамен сдать там не ниже, например, 6, да?
Ну, конечно. Как бы, потому что как бы, у нас были случаи, когда, значит, человек какую-нибудь большую накопленную оценку набирает, и потом к экзамену вообще не готовится, и там готовит только термин. Так нельзя. Как бы, так вы ничего не освоите.
А за термин разве 6 не поставят?
Нет, термин 6 не поставят. Термин могут 0 поставить. Это да.
Справедливо.
Получается, будет несколько экзаменаторов, да?
Ну, конечно, да. Значит, собственно, все те люди, которые у вас вели в течение семестра там, лекции, семинары, значит, вот они все будут участвовать. Так, ну, значит, тогда на этом, наверное, все. Можно отключаться, и кто там хотел отдельные вопросы задать?
Да, я хотел. В общем, я вчера открыл для себя чат магистратуры и узнал, что у нас научный руководитель должен быть на этот семестр.
Вы типа только вчера открыли чат магистратуры?
Да. Он у меня всплыл в сообщении, и я решил все-таки почитать его.
Так.
Да, в общем. Я хотел спросить, мне сейчас просто всем преподавателям написать, у кого места остались, или есть более цивилизованный способ решить этот вопрос?
Так, то есть у вас вообще как бы сейчас научного руководителя нет, так?
Да.
А кто был до этого в бакалавриате?
А мы с ним разошлись.
Однако. Вообще, конечно, это вы серьезную задачку не задали. Потому что, то есть, как бы, так-то вообще, конечно, безусловно, для того, чтобы определиться с научным руководителем, нужно будет как бы написать разным людям и с кем-то договориться. Вот, в плане научного руководства. Другое дело, что сейчас 18 декабря, и уже через неделю вам нужно ставить зачет по спецсеминару и оценку по практике. Как там она называется, забыл.
Трудовая практика?
Ну, в общем, неважно. Короче говоря, по научной работе вашей сделанной за семестр, которой вы как бы вообще ничего не делали. Или вы что-то делали?
Ну, научного руководителя не было, я просто читал всякие интересные вещи, но я не
Нет,
думаю,
ну, может
что
быть,
это
вы
можно
там, я не
научно.
знаю, на работе или где-то там проводили какие-нибудь там исследования или что-то такого.
Нет. Какие там исследования?
Ну, в общем, короче говоря, значит, давайте
Да,
так.
беда.
Так, на сегодня у меня не получится. Значит, давайте с вами договоримся завтра. Мы с вами вдвоем, значит, созваниваемся. Давайте, скажем, 12 часов сможете завтра?
Да, завтра же суббота, 12 часов.
Да, значит, завтра созваниваемся с вами вдвоем, и я вам тогда, видимо, обсудим, значит, чего вы там читали, не читали, и какое-нибудь, может быть, мини-задание выдам на такую, как бы, быструю научную работу, значит, и на зачет по спецсеминару. Вот, и чтобы тогда я тогда в этом семестре это проставлю. Вот. Как бы вы, конечно же, должны, значит,
да, потому что решили эту проблему нормально.
Руководителя. Да.
А не через костыли.
Вот.
Просто как-то никаких разговоров про этого не было у нас в чате, поэтому я не среагировал вовремя.
Я, по-моему, писал его активно, там где-то в октябре или в конце сентября на эту тему.
Нет, я имею в виду в нашем студенческом чате.
Ну, правильно, потому что у всех-то есть научные руководители, все что-то работают, как бы, и никакого вопроса по этому поводу нет.
Да, просто когда был очно, обычно были разговоры про научных руководителей, как все мучаются научниками. А сейчас, очевидно, таких разговоров не было, потому что мы не собираемся особо. И вот я не рассчитал.
Понятно.
Дмитрий Александрович, у меня такой вопрос. Я, собственно, до своего научника не могу дописаться. То есть я написала в течение 2 месяцев где-то.
Это Воронцов, да?
Да. То есть я там что-то тоже читаю, что мне в начале еще семестра, когда мы созванивались, сказал. Но тоже я не могу с ним никак связаться. То есть у него есть еще курс в МФТИ, на который периодически захожу, смотрю его лекции тоже. Но я у него спрашиваю, видел ли он мое сообщение, он говорит, да, я вам отвечу, и в итоге вот так 2 месяца.
Значит, смотрите, как бы в плане Воронцова, значит, так будет и дальше. То есть вам нужно как бы с ним как-то обсудить и попробовать договориться с тем, чтобы он вам выделил какого-нибудь куратора, значит, Артема Попова или там, кого-то из своей команды, вот, с кем бы вы могли вот уже как бы чаще там встречаться, что-то обсуждать, потому что с ним самим напрямую как бы договориться о встрече – это как бы реально непростое дело. Даже я иногда как бы не с первого раза до него дозваниваюсь и так далее. Поэтому как бы вот хороший вариант будет, если вы с ним как-то договоритесь о том, чтобы у вас был какой-то куратор, как промежуточное звено.
Ну, хорошо, но чтобы договориться, надо, чтобы он мне хотя бы раз ответил. То есть я сейчас даже не могу добиться от него, чтобы созвониться или как-то что-то такое.
Ну, во-первых, вы как бы точно, значит, сейчас ему нужно будет ставить вам, во-первых, зачет по спецсеминару раз, во-вторых, вот этот вот отчет по практике, да, 2. Соответственно, тут он в любом случае должен в этом деле поучаствовать, поэтому тут вы с ним в любом случае свяжетесь и вот как бы тут же как бы не забудьте сразу и этот момент обсудить.
Ну хорошо, вот если он мне в течение этих 2 дней не ответит, я могу рассчитывать, что вы поможете мне с ним связаться, я не знаю.
Хорошо, да, тогда мне напишите в начале недели, недельник или там когда-то, и значит, я тогда попробую сам тогда с ним этот вопрос обсудить.
Спасибо большое. Спасибо.